So today is a cool day at MotoIQ because I get to talk about one of my favorite engines, the Toyota 2JZ, 1JZ family. But first, I want to talk about some of the stuff we've been doing at MotoIQ. We have an online store now, so if you go to motoiq.com, go to the upper left corner and there's a shop link. You can click on that and you can buy probably any kind of part that you would want. A lot of the parts are stuff that we talk about in these videos and some stuff that we haven't gotten to yet. The other cool thing is we now have our MotoIQ line of merch. So you can buy the shirt that I'm wearing here. So if you go to our online store, there's a merch link and we have t-shirts, hoodies, and stuff like that. So now, enough of the commercial. And let's get to some technical stuff about these engines. So the Toyota 2JZ and its little brother, the 1JZ, are inline six-cylinder engines. So there's a lot to like about these things. One of them is that they have really good primary balance. The firing goes on 120-degree intervals, and that works out to a really even balance. The exhaust note is a even interval, so that's one of the reasons why they sound so good. It's kind of like half a Ferrari. The sound isn't too much to do with function, but the balance is. So they have really good primary balance. But perhaps the most important thing about these engines is they're built like a brick shithouse. I mean, I'm not kidding. They have a cast iron block, really beefy internals. They don't need too much to make a lot of power. I mean, you could probably get a stock bottom end 2JZ and easily get 600 horsepower pretty reliably on it. You could even go 800 horsepower or even high as 1,000 horsepower for a little while on the stock bottom end. So it's, like we don't recommend going to those high power levels and doing the track day, for instance, but for like a little rip or some dyno stuff, sure, why not? But it's a really strong motor. It's kind of like an old school Toyota. It's built to take punishment. So it doesn't take a whole lot to make these engines reliable and maintain a lot of power. So we're going to go over like kind of a basic 2J, 1J build right here. You don't need to do all these things, but this is kind of like the basic of what's nice. This will probably see it to about 1,000 horsepower. And if you wanted to do consistently over 1,000 horsepower, there's a few other things we would do, but I mean, you can do a lot with what you have here on the table. So the first thing I wanted to talk about is the cylinder head. Here's your cylinder head. It's 4 valve per cylinder, shim and bucket, pretty straightforward. The shim and bucket is a good design for high revs. It's a very simple valve train, so it's really light and can rev high without problems of valve float and stuff. Now this isn't exactly necessary, like we did a little bit of porting, which isn't necessary to make big power, but things that you do like this, if you have the right turbo combination, you can make more power with less boost, which is always good for reliability. So what we did is we did some porting. We kind of blended the seat of the valve into the bowl, and we blended the bowl into the port itself, and we kind of rounded off the short side radiuses on the intake and exhaust. So basically we got rid of the major restrictions. In order to keep like a really wide power band, we didn't take a whole lot of material out. We just took out the basic places where you can improve flow without removing much material. We also went through with a cartridge roll and slightly polished the ports. We didn't really enlarge them, but doing this kind of stuff really increases the flow, really increases velocity, which is important for scavenging, and doesn't really increase the volume of the port, so the velocity stays high. With porting, we also did a valve job. Now we used our signature Newen valve job. where we use the Newen valve seat cutting machine, which is like a CNC machine. So basically it cuts a smooth radius from the combustion chamber to the 45-degree seat. The seat is not a radius seat, it's a conventional flat seat. And then it cuts a radius from the 45 seat into the port. So you have a smooth radius, a flat seat with kind of sharp edges, and the smooth radius going into the port. So we found that generally this is the best for flow. You know, if you don't want to pay us to do bench flowing, this is the job we do, and I would say 95% of the time it gets you way more flow. I mean, there's some engines that might benefit from something slightly different, but we haven't seen that yet, or no one's wanted to pay for us to find out if that's the truth or not. One of the things we do is we also use the Newen machine to unshroud the valves. So we program it to do a kind of a wider cut, so the chamber is kind of opened up in the area of the valve. Now this unshrouding kind of helps low lift flow. So when the valve is opening or closing, it helps. When the valve is in close proximity to the side of the combustion chamber wall. Low lift flow is really important because your valve spends more time at low lift than it does at high lift, like twice the time. So when it's first opening and closing, we pay a lot of attention to the flow at that part of the valve cycle. So we clean up the valves, we check the valve guides. Now if the valve guides are starting to develop play, then we replace them with silicon bronze valve guides. We usually use SuperTech. But one thing about a shim bucket valve train, it has very little side load on the valve guides, so the valve guides last a long time. So a lot of times the valve guides are fine. I would say most of the time the valve guides are fine and we don't have to change them. We didn't have to on this head. For valve hardware on the intake side, we run SuperTech intakes. Generally we run 1 millimeter oversize. The 1 millimeter oversize allows us to set the 45 up nice and high and have a fresh 45 seating surface. Now, when the valves start to get some miles and hours on them, they start to sink down into the head. When they start sinking, the valve kind of has to come out of a little crater before it starts getting into the chamber, and that messes up the flow. So if you can have the 45 as high as possible, like a brand new head, that gives you the best flow. And when we go 1 millimeter oversize, it enables us to cut the 45 further up so the valve is nice and high and we get good low lift flow. It's not so much we're putting in big valves to get flow, like a lot of times on cylinder heads, putting in bigger valves, especially with these modern 4-valve motors. If you go too big on a lot of these engines, you get actually less flow because the bigger valves shroud against the sides of the combustion chamber more. But 1 millimeter is only a little bigger. Lets us get a fresh start with the valve seat. If everything's really, really worn out, we'll have to change the valve seat, but that hardly ever happens, especially with the shim bucket system, because it's so light, runs low tension valve springs. They don't beat up the valve seats much either. Now for the intake side, we run a superflow valve, like I was saying. Superflow valve has some kind of neat features. It has a reduced diameter valve stem at the bottom. What this does is that it helps flow. Now I don't know about this particular engine, but other engines have seen up to 18% gains in flow just by reducing this diameter. I don't have data for this particular engine, but it sure doesn't hurt. So the reduced stem helps flow. If you look at the intake valve, it has a nail head contour, so it's kind of flat right here. So what has been found is on most engines, When the flow is coming in, like on the intake side, having a flat contour helps the flow maneuver around the edge of the valve, through the valve seat and into the combustion chamber easier. When you look at it too, the valve has like a slight back cut to it. So there's like a 30-degree or so back cut before the 45. That also helps the flow turn the corner and helps your low lift flow also. Finally, the valve, the stem and the head of the valve on the inside has a swirl polish pattern, and that's been shown to slightly increase flow as well. So it's a common trick. The intake valves are made out of stainless, so they're non-corrosive and nice and hard, and they won't sink down into the seat too quick, and they'll last a long time. On the exhaust side, we use an Inconel exhaust, also by Supertech. It has some of the same features, like it has a reduced stem. Now the exhaust valve, the stem has to conduct heat out of the valve head because the exhaust valve runs a lot hotter. So it's not turned down as much. It's only turned down a little bit. So I don't think it's going to help flow as much, but you want to be able to conduct heat away from the head. Also, when you look at the exhaust valve, it has like a tulip contour. Now this tulip shape has been found to help flow when the flow is going out of the combustion chamber into the exhaust port. It kind of helps the flow turn the corner up into the port. So it's kind of the difference here. So if you look at the intake and you look at the exhaust, you can see the difference in contour. Also, there isn't a sharp corner here. Like it's not exactly a 30-degree back cut, but because of the tulip shape, just the edge has been broken to kind of help the flow out of the chamber. It's a pretty nice part. So that's kind of like how we do the head. Next is the camshaft. Now they make a whole bunch of different good quality cams for the JZ family. You know, Tomei, Toda, Brian Crowder. For this particular motor, we're using some Brian Crowder camshafts, and these are made on brand new chilled iron billet. What a chilled billet is that when the billet is cast, there's a heat sink called a chill in the mold, and that's right where the lobe is. So what that does is it gives you like a billet that's hard in the lobe, but it's softer in the rest of the cam. So that helps your wear without making the cam too brittle to where it's going to snap. The Brian Crowder cam has about 272 degrees duration and about 10 millimeters of lift. Now it's not a crazy cam, but it's a good solid cam. So if you're doing like a single turbo upgrade, but like a medium sized one, I mean this will really go. I mean it'll make 800 horsepower, no problem, and with a really nice power band, especially if you do a twin scroll exhaust manifold and a twin scroll turbo, it'll spool really quick and be really pleasant. We're also running Brian Crowder valve springs and Brian Crowder titanium retainers. Now the titanium retainers are good because they're half the weight of steel, but they have similar abrasion resistance characteristics. Some people run aluminum retainers, but they tend to chafe and wear quicker. I'm a big proponent of matching springs and the retainers, matching that to the camshafts. So if the manufacturer says run X spring and X retainer, I try to keep that all matching. A lot of that is due to their harmonics. A lot of people mix and match valve train parts, but I always found that that's not a good idea. A lot of cams are ground specifically to have a certain jerk and a certain ramp acceleration, and a lot of that is tuned around the harmonics of the spring. So it's pretty complicated math, and I don't want to get into it here, but a lot of times the cam profile is designed to be the most aggressive that you can be and not overly excite the spring, so you don't get into spring surge. A lot of people call it valve float, but technically it's surge. And a lot of the better manufacturers design their cams to get out of the surge area, and it's all tuned as a single unit. Now, a lot of cheap cams, they just use some blank off a small block Chevy or something and scale it up and down, and your harmonics are totally inappropriate, and you're not getting the most area under the lift curve for, like, if you use like a Chevy load profile on a shiv and bucket valve train, it would be really crappy, and you probably wouldn't get much area under the lift curve, and you wouldn't have much surge margin either. Now, one of the tricks that are kind of common in these motors, the stock follower is a, what do you call it, a shim over bucket. So it uses this bucket that sits on top of the valve and the spring. Then you get the select fit shim to adjust your valve clearance. That's all fine and dandy, but at high RPM, or if you're running a higher lift cam, the lobe of the cam tends to like flip this thing out like a tiddlywink, and then you develop all kinds of lash, and it beats around, and you'll probably end up dropping the valve, and then surely you destroy your cam and the bucket. So to avoid this, we run a newer Toyota one-piece follower. Now this whole unit is select fit. This one is like out of a 2AR engine, but generally any of the newer Toyota 4-cylinders will work on the J series of engine. And these are select fit, so you get whatever thickness you need. There's a little nib in there that's different heights for the different thicknesses. So you have nothing that flicks out, nothing that can cause total destruction. It won't come out. And it's a heck of a lot lighter. It's probably, I don't know, 50% lighter than the old way of doing things. We also use adjustable timing gears. Now, the HKS ones are pretty popular. I don't know if they're better or worse than anyone else's. I mean, they're all kind of about the same, but they're this cool purple color that people seem to like. So if you see the 2J behind me, it has them. It seems like everybody with a 2J gets these, but this is a JDM version of the motor, so it has variable intake cam timing. So this is the stock variable cam timing sprocket. Just painted this part purple, so it matches the HKS thing, but that has nothing to do with anything. That's just for looks. It even kind of matches, so cool. So it's basically a very simple, it's a very simple head, just good solid basics, no fancy CNC porting, just basically a cleanup job. We call that pocket and entrance porting, by the way. Nothing fancy, it'll get you a long ways towards making that 1,000 horsepower. So now on the bottom end, this is one of the main reasons why this engine's so successful. I mean, it's built really stout. Like the stock crank is a forged part. It has a lot of journal overlap. Now, when we talk about journal overlap, I've been throwing that term out a lot in our videos, but I realized I never explained what it is. Basically, you have your main journal and your rod journal, and in between, the overlap is the amount that the two journals overlap. So if you have a lot of overlap, it really helps the strength and rigidity of the crank and its resistance to torsion. Now, the 2J has pretty much right-sized journals. Like they're a good size to make a good strong crank. It has good journal overlap for strength and stiffness, but it's not so big that your bearing speed gets too high. So if your journals are like super huge, at the interface between the journal and the bearing, what you call your surface speed goes way up. And when you have a really high surface speed, the hydrodynamic layer of oil between the journal and the bearing is really sheared. So that does a couple of things. It's hard to maintain a good hydrodynamic film when the surface speed is really high. It also heats your oil a lot, and it also creates a lot of friction. So there's like a trade-off between strength and bearing speed or surface speed in that hydrodynamic interface. So the 2J is a pretty good compromise. You know, being an inline six, it's subject to second order harmonic twisting. So what that means is it's subjected to whip, and the whip starts to become an issue maybe around 7,500 RPM, and it kind of peaks at 8,000. And at 8,000, there's like a natural wave whip going through the crank that can actually cause it to fatigue and break. That's probably why you shouldn't rev a 2JZ past 8 very much, at least if you're doing something like drifting or road racing where you spend a lot of time at higher RPM, like a lot of time on the limiter or like just hauling ass on the track. For drag racing and short duration driving, you can get away with a lot more, but for anything that has to endure and be actually driven really hard, don't recommend revving it too high. The other thing I really recommend on these inline sixes is, you know, the stock crank's pretty good, the stock balancer is okay, but if you're going to be driving hard, I really recommend a high quality harmonic balancer. This helps attenuate that whip. This is a fluid damper. We did a cool video on how fluid dampers work, but basically it's a viscous damper. So there's an inertia ring floating around in a silicone fluid. What we like about this damper, particularly on the inline six, is the harder the crank whips, the more the balancer works to damp out that vibration. So the nature of it is instead of having an elastomer and a friction ring that's kind of tuned around a specific RPM, with the fluid damper, the more the crank whips and the more it torsionally flexes, the harder the damper works to protect the engine. So inline sixes get a quality damper. Our preference is fluid damper, but there's other good dampers out in the market, and the stock one's not too bad. But this isn't an engine that you want to take off the balancer, stock balancer, put a lightweight pulley on, or a solid hub pulley. I don't recommend that for harder use. Now, if you want more displacement, there's many companies that build high quality stroker cranks. You don't need to do this to make big power, but if you want to make more torque, for instance, like they have 3.2 and even 3.4 liter stroker kits. My personal opinion is maybe 3.2 is a happy medium, and you don't want to stroke it too hard because your piston speed starts to go up and your journal overlap and stuff start to go down. So you're trading off some of your revving ability to get more displacement. So to me, 3.2 is a kind of a sweet spot. Other engine builders may tell you something else, but some smart guys might say that. That's okay, but this is just me. Stock crank is also fine. You know, it's a good part. So here we are, stock crank. What we've done is we've chamfered all the oiling holes. We micro-polished the journals. Since this is a used crank, we magnafluxed it to check for cracks. It's been balanced. It's ready to go. One of the other things you can do is cryo and WPC the crank. You can WPC the block, the rods, the bores, the camshafts, the valve springs, but this customer didn't pop for that. We think cryo and WPC really helps if you're a hard use guy, like you're actually doing track days, actually drifting, actually racing, you're doing drift competition, then we feel that these treatments work. The other time you'd want to pop for the expense of all that is you want to build this engine and have it last as long as possible. So those treatments actually help wear and tear. So we'll be getting into that a little bit more in just a second. I guess next we're going to be talking about connecting rods. These are Brian Crower connecting rods. The rod is made out of 4340 billet. Now this is a like a chromoly kind of alloy, but think of it as chromoly with more nickel. The nickel gives it a lot of toughness and impact strength, which is the kind of stress that a connecting rod sees. So connecting rods, cams, gears, this is a really good metal for that. It's machined out of a billet of the stuff. It has ARP 2000 bolts. So I put my glasses on and I noticed that these rods actually have the optional 625 bolts, not ARP 2000. Now, the 625 alloy bolts are my favorite bolts. They have a 280 psi tensile strength versus 220 psi for ARP 2000. And they don't have the corrosion sensitivity of an alloy like L19, which is another ultra high strength alloy. So 625 custom age ARP bolts to me are the best, and these rods have them. It's machined to where it's within less than a gram of weight. We go ahead and we do our own balancing on it to get the balance within 1/10 of a gram. The rod is actually shot peen from Brian Crower. Shot peening is bombarding the surface of the material with perfectly spherical hard iron balls. Now what this does is it puts a compressed layer with compressed stress over the whole surface of the part. This greatly improves fatigue strength, like generally about 100% on steel-based alloys. So it's something for nothing. You shot peen it, you double your fatigue strength, and it's actually not that expensive of a process. So you get something for nothing almost. The shot peening makes the surface so it's hard for a crack to propagate. Think of it as a thin mini forged layer over the whole part that's hard to penetrate, hard to get a crack started in, and that's what shot peening is. It's kind of like WPC, but on a deeper scale with bigger media and more impact. And you can kind of see this pebbly texture on the part, and that kind of gives the way that it's been shot peened. Another cool feature of the rod is twin oilers and a oiling groove in the small end. So the oiling holes are kind of like on the side of the rod here. I always prefer that. A lot of manufacturers put the hole on top, but on top is a pretty highly stressed part of the rod because when you're at high RPMs, this thing's under tensile stress. So you don't want to put a big hole here. Two small holes here weaken the rod a lot less. And they also probably pick up splash a lot better. So the oiling holes pick up oil and feed it into this groove that keeps your piston pin lubricated. Next are the bearings. We like to run King XPC if they're available for the engine. Now they're a tri-metal bearings, so you have a copper lead kind of underlay. It's copper lead and a bunch of other alloying things, but it's a hard underlay that can take a lot of load without flaking and squishing out. So it has a high load bearing capacity. One of the bad things is it doesn't have much embeddability. So this isn't the kind of bearing to use if you never change your oil and you don't maintain your car well. But for a racing motor that gets the oil changed all the time, these things have a really good load bearing capacity. On top, there's like a slightly softer, mostly zinc layer on top of the harder underlay. This helps your embeddability, but it's not very thick. If you make it thick to be able to embed more debris and contamination, it squishes out, it's a soft layer, and it reduces your load-bearing capacity. So it's a lot thinner than like on a stock bearing, for instance. So change your oil a lot when you run these. And actually, any high-performance bearing can't tolerate dirt very much compared to a stock bearing. So that's a rule of thumb. You got to keep that oil clean. Finally, this has King's coating, and the coating is a polymer which helps the slipperiness, but most coatings on bearings are just a layer of slipperiness, and they're there to protect the underlying bearing material in case you have a momentary dry moment and you get metal-to-metal contact. But on the King bearings, the coating actually contains a lot of copper nanoparticles, and that gives the coating a lot of hardness. So the coating itself increases the bearing's load-bearing capability by about 15% or so. So it's a pretty innovative coating. It's cool. It's one of the reasons why we like these XPC bearings. Now we like Cleveite tri-metal bearings, and we also like ACL bearings. They're all use that same kind of tri-metal technology, and they're all really high quality, and they all have really good track records. So if we can't get Kings, we use Cleveite or we use ACL. And all of those are good bearings. We don't hesitate using any of those three. Finally, with the pistons, we're using Wiseco's in this case. Now these are Wiseco's designed specifically for turbo use and the 2JZ, and they're pretty beefy. So if you look, first you can look at the piston pin. The piston pin is beefy and thick. For turbo motors, you always want to go to a thick pin. You don't spin the turbo motor as fast as you do a naturally aspirated motor, so the reciprocating weight isn't such a big deal. But your cylinder pressure is really high. And if you run a thin, lightweight piston pin, what will happen is it'll flex, and it'll flex like a U, and the piston pin will actually grab the edges of the bushing on the small end and seize, and then cause the bushing to spin in the rod, and then usually something breaks and bye-bye engine. So turbo engines, nice thick pin. Now these pistons also have the number one ring moved pretty far down, so look how thick that ringland is. It's about a 1/4 inch almost, and even in the thin areas around the valve pockets, it's still pretty thick. So that gives you a lot of beef. You know, turbo engines, sometimes they run close to the edge of detonation, and you can pinch a ringland, and then that's usually a disaster. Ringland digs into the cylinder walls, you lose your compression, you damage your cylinder walls, you damage your piston. The pistons get damaged anyway because the ringland's crushed. But this is a turbo motor that's not going to happen unless something really bad happens. You know, this is a really thick ringland, more than typical. The pistons itself has a pretty high dome, so I assume this has a higher compression, and the customer's going to do something like, he's probably going to run E85 or racing ethanol or something, so you can get away with a higher compression with boost. It's one of the tricks we do. I mean, we run 11 or even 12 to 1 if the engine's only going to be run on ethanol. If it's street E85 from the pump, maybe 11 to 1 is what we keep it at. But let's say you're running a race ethanol like a E98, like Ignite Red, we go 12 to 1 even, and absolutely no problem. Ethanol has really high octane, and it has twice the specific heat of gas, so it sucks the heat out of the engine. A lot of times if you're running race ethanol, you can advance the engine until the power falls off, and it still won't detonate. It's good stuff. Now, you might have seen our video about E85 sucking, but that has nothing to do with racing. For racing and boost, ethanol is a damn good fuel. Other features on this piston, It has differential skirts, kind of like a FSR JE piston. The thrust side of the piston is a lot bigger than the non-thrust side. The thrust side is the side that gets dug into the cylinder wall on the power stroke. So you want more surface area to support the piston. On the non-thrust side, it can be a lot smaller, so you have less friction and less weight. You can see the differential skirt right there. That's a really cool feature. I love it. The piston boss on this piston is very sturdy, and it has a lot of area. A lot of that's to support the pin under a lot of boost pressure. And when you look at this piston, I mean, the skirts and the boss area and the underneath the undercrown area are all thick and beefy. So this piston is designed to withstand a lot of boost pressure. I really like it. Now, when you look at the ring grooves, so your number one ring is for a thin, low tension ring, and you have all these little holes for lateral gas ports. So these little holes here, combustion gas can go through these holes, goes behind the ring, and pushes the ring into the cylinder wall, so you get better seal, especially at higher RPM or higher piston speeds. So they call these lateral gas ports. This piston has them. Surprisingly, this piston doesn't have a pressure equalization groove. Now, I don't know Wiseco's reason for that, because just about every piston I've seen that's a modern design has a pressure equalization groove, but the Wiseco doesn't have one. There must be some reason. I haven't talked to their engineers about it, but I mean, that wouldn't discourage me from running this piston at all. I mean, this is a nice part. I really like it. The piston is also nickel plated. Nickel plated kind of helps protect against some of the flash temperatures that you might get with flash detonation. It's also very slippery, so it's kind of like a anti-seize. It's slippery in the ring grooves, and it's slippery on the skirts. And this has like a polymer coating on the skirts too. And this kind of helps prevent like any kind of bore scoring or anything, and it also reduces noise somewhat. So I'm pretty impressed with this Wiseco. I'm only curious why they don't have a pressure equalization groove, but to me it's not a huge issue. I mean, the rest of this piston is awesome. So I totally forgot to talk about the material of these pistons. We use 2618, which is a low silicon alloy. It's ductile, it's strong, it can take detonation and heat. Its only drawbacks is it expands more, so you have to run a little bit more piston to wall clearance. It's a little bit noisier, but hey, with a stout iron block, you're probably not even going to notice. And you know, we're not messing around. We're trying to make horsepower, not make a luxury car. So 2618 was our alloy of choice. Now there's other alloys you can use if your requirements aren't exactly that, but that's the subject of a whole nother video, and we'll probably make a whole nother video about that subject. For piston rings, you have a very thin 0.8 millimeter ring, so this is going to make really low tension. It's probably one of the reasons why you have the gas porting on the number one groove to help this thin guy seal. The thin guy is like it's like a chrome ring, really thin, really low tension. The chrome's going to give you good wear resistance. The second ring is a iron ring with a Napier profile. Napier profile, they have like a little hook in the end. This little hook helps scrape any oil that makes it past the oil ring off the cylinder wall. It also has a really thin area, so it seats in, breaks in, and gives you a really good seal really fast. The iron's a little bit softer, and it kind of breaks in and conforms to the cylinder quicker than the hard chrome top ring. The hard chrome top ring is for wear resistance and to take the heat of detonation and everything better. Oil ring is a thin, low tension ring, kind of like state-of-the-art modern technology. Pretty good stuff. The ring should seal really well, last a long time, and have really low friction. So that's about it for the guts of the engine, and I guess we'll talk about the block next. So one of the secrets of the 2JZ or the JZ's family strength is the iron block. Now, iron is a pretty good material for blocks. I mean, it sounds old school and heavy, but it has a lot of advantages. One of the advantages of iron is it's twice as stiff as aluminum. So when you're talking about issues like main cap flexing and the block flexing and losing ring seal and causing internal friction and wear and things like that, iron does it a lot less. These blocks can take 1,000 horsepower, no problem, and they don't require too much. Now, what we did is we have ARP studs. When you put studs in the block and you're changing the torque, you have to have the block resized because it distorts slightly differently than the stock bolts. So when we're studding the bottom end, we resize everything. If we're not using studs and we're using the stock bolts, what we do is we check to see if it needs a line boring, and we do if it needs it. Now, these blocks are so tough that they don't need a line boring very often in this way, but we align bore all the ones that we use studs in. A lot of these race bearings, the stock Toyota bearings come in like maybe 10 different combinations of sizes that you can use to set your clearances just right, but these race bearings come in like 2, so in order to control our clearances a lot more, the align boring is kind of important in the overall crank size and everything. So that's one of the things. Studs, align bore, stock bolts, check. Maybe some of the tricks we do is we get some cartridge wheels and we kind of lightly go over the inside of the block. Iron blocks are usually sand cast, and the sand kind of sticks to the iron kind of and is loose. And sometimes the sand can break loose and go through the motor. So we usually go over everything with some cartridge wheels and maybe a die grinder. We deburr everything, knock off the edges, and take some of that entrapped sand out. I mean, we don't polish it like chrome, but we just kind of go over it a little bit. That's a good deal to do on any kind of iron block. You don't really need to do it on aluminum blocks, but iron blocks, that's the thing. Now our bores. Modern piston rings need a really good bore finish, so we use like a kind of a finer diamond stone to do the final honing, and we do a step called plateau honing. So this uses a cork bonded stone, and what it does is it knocks the points off of the honed surface, so it gives this smooth, lustrous finish. And you still have the honing marks that are kind of deeper that hold oil to keep the rings lubricated. And having some deepness to the honing pattern is important on the turbo engine because the rings are subjected to more combustion pressure and stuff. So this is something that a lot of maybe not so experienced or local engine builders or something, they aren't aware of, and they don't spend as much time, getting the right bore finish, but we do. Now, if we're going to be using this for drifting or track days or road racing, we WPC the bores and we'd probably cryo the block. But this customer, although he's building a really nice, solid motor, didn't opt to do that. I mean, there's nothing wrong with it. The 2JZ will do you right. But it's something we would do for like hard use and real competition. Now, if you wanted to go to really sick horsepower, like beyond 1,000 and really hard use, there's things you can do like billet main caps to stiffen up the bottom end. You can even get a dart block. The dart block has all that stuff built in, and it's a lot stronger, thicker deck, thicker cylinder walls. The dart block can hold like 2,500 horsepower supposedly. You know, like up to 1,000, no problem for the stock block with just some simple things like studs. If you want to go a little higher, billet main caps, just needs a little bit more machining, but that's what I love about the 2JZ. You can put a ton of horsepower through them. You don't need to do that much. And even the stock bottom end ones do pretty damn good. You can do pretty damn good with just pistons, rods, bearings, good machining and assembly. But, you know, like we like to build something like this that good solid, makes more power with less boost, and just has that little bit of extra strength. But you don't have to do that. 2JZ does that for you. So if you like this content, be sure to subscribe, give us a like, go to MotoIQ.com. You can read our millions of tech articles on there, 10 years worth. There's probably something that everybody would like on there. If you want us to build an engine or do some stuff on your car, you can hit that garage services, fill out the form, and we'll get back to you. Thank you for all your requests. You know, we really appreciate your business. If you want parts and stuff or our merch, go visit our web store. It's at the top of our page to the left. It'll say shop new or something like that. Click on that link and it goes to our web store. So that seems like a commercial, but you know what? It kind of is. So until next time, we'll be talking to you soon, I guess.